You're here because you want to master metals in the Reactivity series with a University of Cambridge graduate. This is actually part 1 of our Reactivity series lecture videos. If you want to watch the future videos, be sure to check out our playlist in the link below. Hi, I'm Brendan, and I'm a University of Cambridge graduate who has been teaching chemistry to many students like you over the past 9 years. I'm also the founder of the Chemistry Institution, where we have helped many students improve in a short amount of time and achieve the grades of their dreams. Be sure to check out our website in the link in the description below so that you can download a free copy of the notes for yourself and use it to run through this lecture with me today. In this Reactivity series chapter, you will learn that all your metals are not equally reactive, and so they can be arranged actually in the order of their reactivities. And generally, a metal higher in the reactivity series will do the following, right? They will react vigorously and quickly with chemicals to form products, right? They can also corrode more easily, right? They can also lose electrons more readily to form positive ions, and they are also more stable to the action of heat on its carbonates. So for example, potassium carbonate is very stable compared to calcium carbonate because potassium is just in general more reactive. It is also extracted from its oxides using electrolysis, right? And it is not possible with simple reduction methods using carbon and or hydrogen. So while these are the observations we make for metals that are more reactive, right, we actually can do a deeper dive into very specific metals and their specific reactions as well. So the reactivity series can be used, right, in predicting what chemical reaction, if any, will happen. Okay, you can also predict the stability of metal compounds. You can also predict how to extract the metal, and you can also predict whether it can be used to prevent rusting or not. Let's start with the reaction of metals with water and steam. So your metal, right, if it's reactive enough, it can actually react with water, alright, and it can form the metal hydroxide and hydrogen gas. Or on the other hand, metals can also react with steam, which is definitely more favorable because steam is at a higher temperature, right, and it's in the gaseous form. So if metals react with steam, you could also form the metal oxide and hydrogen gas. So in this table on the right hand side, you will see the list of metals all in the reactivity series, for the top being the most reactive metal and the bottom being the least reactive metals. And it will do a comparison of what kind of reactions these metals will have with water and steam. So with cold water, if you look at potassium, right, it will also have an explosive reaction. And of course, if it has an explosive reaction with cold water already, you can already expect steam to also have an explosive reaction as well, right? And it generally follows this equation of here where potassium, right, reacts with water to form the metal hydroxide, which is potassium hydroxide and hydrogen gas. So please memorize this. Next, sodium, right, is a very fast reaction that still often explodes, right? And in steam, alright, it is definitely a faster and more explosive reaction. And the equation is sodium reacting with water to give sodium hydroxide and hydrogen gas, right, as predicted by the equation from before. Next, we look at calcium. So calcium has a very quick reaction where it forms plenty of gas bubbles, right? And these gas bubbles are actually the hydrogen gas that we know is going to be formed, right? And in steam, okay, it's going to have an explosive reaction. As expected, it's going to have a more vigorous reaction. So calcium can react with water, okay, to form the calcium hydroxide. Next, you have magnesium. And this is where the reaction starts to get less and less vigorous. So you see magnesium in cold water, right, doesn't really have a reaction, okay, with only a few gas bubbles that are produced very slowly. So it still reacts, but it's at a very slow rate, right? So you see the magnesium reacting with water to form magnesium hydroxide and hydrogen gas. But under steam, okay, of course you will have a vigorous reaction, okay, where the heated magnesium burns and you actually get a very bright flame, right? So this magnesium can react with water in the gaseous form to form magnesium oxide and hydrogen gas. Even lower in the reactivity series, we have zinc. Zinc, okay, has no reaction with cold water, but under steam, it still reacts readily, okay, and the heated zinc will burn and produce a very bright flame. So zinc will react with water to give zinc oxide and hydrogen gas. Next, we move on to iron. So iron has no reaction with hot or cold water, okay, and it has a very slow reaction, okay, with your steam. Okay, and the temperature must be indeed very high such that your iron burns red hot. Okay, so your iron can react with water, which is steam, okay, and produce this Fe3O4, which is the oxide of iron, and hydrogen gas. And lastly, all the way down in the reactivity series, your least reactive metals, your lead, your copper, your silver, generally it will have no reaction, okay, with cold water, hot water, or steam at all. Next up, let's look at our reactions of our metals with dilute acids. So only metals above the hydrogen, right, in the reactivity series will react with your dilute acids. So this is the key rule into understanding or to be able to apply whether your metals are able to react with the dilute acids or not, and to what extent. So generally your metal, as we know, can react with dilute acids if it's reactive enough to give salt plus hydrogen gas. Recap, this is actually an equation that you've learned in your acids, bases, and salts. So metals below hydrogen in the reactivity series, like copper, silver, and gold, these will all not react with the acids. So below is a table where you have to memorize, okay, and figure out what kind of reaction that each of the metals in the reactivity series will have with the dilute acid. Unsurprisingly, we know that potassium and sodium will have an explosive reaction because they are very high up in the reactivity series. So your potassium will react with, for example, hydrochloric acid to produce potassium chloride and hydrogen gas. Sodium will also react with hydrochloric acid to give sodium chloride, okay, and hydrogen gas. Now let's look at calcium and magnesium, which is a bit lower down in the reactivity series. So your calcium and magnesium both still have a very fast reaction with plenty of gas bubbles produced. However, it's not very explosive like sodium and potassium. So again, the metal is just going to react acid and you're going to produce the metal salt, just like calcium chloride or magnesium chloride, and you'll also get your hydrogen gas. Next, if we go even lower in the reactivity series, you'll see zinc. So zinc, alright, still has a very quick reaction with plenty of gas bubbles that are produced. Okay, it's definitely less vigorous as compared to magnesium. Okay, and again, the metal is just going to react with the acid to produce the metal salt plus the hydrogen gas. Then we have iron. Iron, right, gives a slow reaction with cold acid, okay, and becomes quick when it's heated. So this will generally produce your gas bubbles and pale green solution. Alright, and this pale green solution is actually the iron salt that is produced. Lastly, you have copper and silver, and as mentioned, because they are below hydrogen in the reactivity series, they are not going to react with dilute acids, whether it's cold or whether it's hot. Now let's go through some important tips. So there are some reactions that are a bit tricky. For example, lead reacts briefly with your hydrochloric acid and your sulfuric acid before the reaction stops. Now, you might be thinking, why is this the case? Because the lead is above hydrogen in the reactivity series, so it should react with dilute acids. Well, the problem is because your lead-2 sulfate that is produced or your lead-2 chloride, both are insoluble. And to know this, obviously, you have to go and memorize the solubility table. Now, your lead-2 sulfate and your lead-2 chloride, okay, will form this insoluble layer around your lead, okay, when it's produced, and it will prevent any further reaction of acids with the metal. So this is a very common occurrence, especially when you're producing a solid from the reaction, and one of your base reactants is also a solid. Copper will also usually not react with your acids because copper is lower than hydrogen in the reactivity series. But copper can actually still react with nitric acid, especially when it's more concentrated, to form your copper-2 nitrate, okay, nitrogen dioxide, and water. So do take note, this usually only happens when the acid, okay, is more concentrated. This is because when your nitric acid is concentrated, it can act as a very strong oxidizing agent. So this reaction actually just becomes more of a redox reaction instead of an acid-metal reaction. Last tip, your aluminium, when it's used, actually doesn't react with water or steam because if you think about it, your aluminium is usually covered by this layer of aluminium oxide. Okay, this oxide is very insoluble in water, and in general, it makes aluminium very passive. It's also very naturally formed because aluminium can easily get oxidized by oxygen in the air to form this aluminium oxide. Okay, and only when your aluminium is added to your dilute acid, the oxide layer will slowly dissolve and this will expose the metal, right? So the metal can then, after that, react with the acid and you can then get your metal salt plus your hydrogen gas. That's all for today's video. If you really learned something and you like this video, be sure to click on that like and that subscribe button so you don't miss out on free content like this. If you want to join my community of students at the Cambridge Institution, be sure to check out our link in the description below so that you can sign up for a free trial class today. Here you can learn the exact systems that we use at the Cambridge Institution to help our students improve in a short span of time and also achieve their grades of their dreams in the end.